I'm going to talk about writing greener Java applications. I think hopefully it's kind of obvious why this is interesting and important. But for us in IT, I think it's extra important. Because when we think about what industries are responsible for carbon, what industries are using energy, actually, a lot of it is coming from the digital world. It's coming from the IT industry. So if you look at the digital world as a whole, and so that sort of includes things like end user devices, it creates more carbon emissions than aviation, which is maybe not what you expected, because we always sort of think of flying as, flying is the poster child for being environmentally irresponsible, and us, we're just here programming our computers. But those computers are actually responsible for a lot of carbon. If you look at maybe what we're more directly responsible for, which is software running in data centers, it's still really a lot of electricity. So data centers use as much electricity as kind of a medium country. So that line there is this line here, the green line, is the data centers. And you can see it's sort of a little bit less than the UK, but more than South Korea. If you think about not just the data centers, but also the network traffic, which I think you kind of have to consider as part of the responsibility of the software we write, the data coming in and out of the data center, then you're looking significantly more than the UK. You're up to about 2% of the world's electricity. So that's kind of bad. And I think there's a natural response to that, which is to go, we're responsible for the software that's using all of the world's electricity and emitting all of this carbon, and this is kind of terrible, and I feel quite anxious. I think that's the sort of the end of the world that I've mentioned. I think there is another response, though. I don't think we need to be so gloomy about it. And I think instead of focusing on guilt, and instead of focusing on catastrophe, we can focus on solutions, because there are actually a lot of solutions out there. And so then the next question is, okay, I'm going to look at the solutions. What should I be doing? And the answer to this, at a high level, is also pretty easy, because then it's, well, should I be reducing my greenhouse gases? Should my organization be reducing our greenhouse gases? And the answer is, duh, yes. And there's so many reasons to do this. One is it's just the right thing to do, but there's also a lot of business benefits. So it tends to bring lower costs. It also tends to bring a competitive advantage, because increasingly now, businesses have to report their carbon footprint. They have to report their sustainability credentials. And every organization is trying to do what it can to make sure it's got great sustainability credentials. And if you have those sustainability credentials, that's going to be an advantage that just sort of ripples through the supply chain. It's also quite good for recruitment. So a lot of people would prefer to work for a company that isn't destroying the world. And so when you're sort of, you're talking to your management about like, why should we do this? That's the slide to show them. So then the next question is, okay, I am sold. I would like to save the world, please. Thank you very much. In concrete terms, what do I do? A resource that I find quite useful, sort of, is the Principles for Green Software Engineering. So this is kind of the standard resource for, okay, if we want to do green software engineering, what should we be looking at? If you actually scroll down on this page, you get to about 8 bullet points. And I think it's actually not super informative. So I've tried to put these bullet points, is anybody able to read that? No. So the good news is that even if you could read it, it's only limited in how informative it is. There's a lot of bullet points there, and there's a lot of things to look at. And I don't know about you, but 8 things is about 4 more things than I can actually hold in my head and think about at once. So I find it useful to have this as the kind of the theoretical model, but then in terms of what I'm going to think about in my day-to-day job, I sort of put it to one side and go on to simpler things. Like wine. So the first step is look at the electricity source for your compute. If it's coming from burning coal, that's bad. A lot of electricity still does come from burning coal. If it comes from burning natural gas, that's pretty bad, but not quite as bad as coal. The ideal is coming from a renewable source like solar, like wind, like hydro. And what usually is sort of a good determinant for the electricity source is your hosting region. So in general, every country, for various historical and political and geographical reasons, has an energy mix that is typical of that region. And so if you choose the right region, you are usually going to get an energy mix that is renewable, that is favorable. Maybe not 100% renewable, but you'll be moving in the right direction. And one thing with this that I want to focus on in particular, because there's a lot of hosting regions in the world, but one that a lot of us use as a default is US East 1 and its friends in Virginia. So Virginia has a huge industry of data centers for historical reasons, which is that the transatlantic pipe that carries all of the internet traffic comes out in Virginia.
If you're exhausted before you even get to your desk, then check out tcube co-working space. Located at O'Connell Bridge in Dublin city centre means a maximum walk of just 3 minutes from over 100 Dublin bus routes, Dart Station and both Red and Green Lewis. And after a long day of code crunching, getting home or meeting friends for dinner is also a breeze. We offer a low-cost, no-frills model, which means you're not paying for free stuff that you'll never use. tcube offers a range of flexible daytime and 24/7 options, meaning you can join our community of freelance and remote software developers from as low as €277 per month. And that includes VAT, coffee and 1 gigabit Wi-Fi. So if you're looking for a distraction-free workspace, which you can come to and then get out again to enjoy your life in the comfort of knowing that you've been at your most productive, then get in touch today for a free trial. Call us on 675-9777 or find out more online at tcubedublin.com.
And then it had another natural advantage for data centers, which is that Virginia has a lot of coal. And so data centers need power. And so they said, we've got the data, we've got the coal, let's build lots of data centers. What could possibly go wrong? I think now it's pretty obvious what is going wrong, which is that now we have all of these coal-powered data centers. And traditionally, like many regions, there's one company which has a monopoly on power generation in Virginia. That company has been quite reluctant to do anything other than coal. That is changing now, I think, because of consumer pressure. People are talking to their cloud provider and saying, I'd quite like to run in US East, but I would quite not to be running on coal. Could you please talk to the power company? And so things are shifting, but they're shifting very slowly. So one easy thing that you can do is don't run your workload in US East 1. More generally, look at the sustainability information for the region before choosing that region. Sometimes it's quite surprising what's green and what isn't. If your cloud provider doesn't make that information available, if it's quite hard to figure out the energy mix, the sustainability footprint for the regions, maybe that's a good reason to think about choosing a different cloud provider. This is something where us as consumers and the pressure that we apply can make a big behavior difference. So use that consumer pressure to go to cloud providers that are publishing the carbon footprint for the regions, and then choose a region that is green. So that's the easy one. I think that's really kind of, it's so transparent to move workloads between regions that you can just do it, and then you're in a good place. The next one is a little bit more complicated, but I think perhaps more interesting. And this is my sort of condensing of the green software principles down to just 4, which is the amount that I can hold in my head. So there's sort of two parts to it. One is thinking about the infrastructure side. What's going on with my platform? What's going on with my hosting? What's going on with my hardware?
Partnering with Amazon Web Services, Global Payments is transforming our issuer platform to deliver innovative payment solutions at scale in a secure cloud-based environment. From enterprises to small and mid-sized banks, and from new fintech entrants to embedded payment service providers, we are bringing world-class capabilities like program management and banking as a service to new markets globally. At Global Payments, our unparalleled legacy of reliability, performance, and experience, combined with AWS's cloud leadership, will meet the increasing demand of a connected digital world. That's Global Payments. That's innovation that delivers.
In there's 2 things to think about, really. One is elasticity. How easy is it for me to scale a workload up and scale it up and scale it down? The other is utilization, and that's quite closely related to elasticity. And utilization is, how much of this computer am I using? Did I just provision a €1,000 Kubernetes cluster and then leave it running with no workload for 2 months? Because the utilization of that cluster was 0, which is kind of terrible, because it meant that all of that hardware was wasted, and all of the electricity just to keep the cluster running at idle was wasted because I didn't actually have any workload on it. So what you want is, elasticity helps you achieve utilization, because had I had more elasticity, I could have fixed that bad utilization. But because once I'd provisioned the cluster, I wasn't going to deprovision it until I needed it, because it was work to provision it. So I wanted to keep it running in case I needed it. So if you have good elasticity, if it's really easy to get things up and down, it means that you can only run what is needed and you can have better utilization. The other thing to look at is the actual software you write, the actual software you run. And there what you're really looking at is efficiency. But with both of these, there's this sort of overarching consideration as well, which is utility. And what I chose U because it sort of matched utilization and it kind of gives like all of the vowels. But what we're really looking at here is value. Is this workload useful to someone? Or is it my Kubernetes cluster that I forgot for 2 months that isn't actually doing anything useful to anybody? Is it a build that I kicked off, but I don't actually care what the result is, and it just churns away for several hours anyway? Another classic utility problem that we see is a lot of times, if you want to hear a song, the easiest place to find that song is on YouTube. So you go and you play the video of the song, and then you go and you do something else, and you don't actually watch the video, you just listen to the song. But the streaming is where the bulk of the carbon footprint of playing that song comes from, and it was wasted. So it's about trying to think, is somebody getting something out of this? Or is this actually just useless? And trying to trim down things that are useless. And you can make a big difference with this. So I saw a talk from Chicago DevOps Days, and it was about managing your AWS bill in general. But one of the things they did was they realized that they were only working in one time zone. And they used things in the day, and then they went home and they did not use them. So why were these things up and running? And they wrote some scripts to just take their AWS instances down overnight, and their cloud bill went down by 30%. So they were thinking about it in terms of cost, but there's also a carbon impact there, which is this little piece of scripting made this big change to their carbon footprint. The next one, you've seen this before. This is the return of the zombies. So 25% of the servers were doing no useful work. That means 25% of the servers were wasting carbon, were emitting carbon for no value to anybody. So a light switch, I think, is kind of the ultimate model of elasticity. I noticed earlier I went up to use the loos, and I don't know if any of you did as well. I would have taken a picture of it, but I didn't bring my phone with me because I don't bring my phone to the toilet. And there's about 4 flights of stairs between here and the toilet, so I was too lazy to go back and get it. But in the toilets, there's a little sign that says, "Be climate friendly, turn off the lights," because it's a manual light switch. And I think most of us are really okay with that, and most of us would probably now do that kind of automatically. And most of us wouldn't think, if I turn off the lights, will I ever get them back on? Because we have a lot of confidence that, you push the button and the lights turn off, you push the button and the lights turn on. We don't sort of say, okay, I'm just going to leave the lights on just in case they don't come back.
In 2019, there were more than 5,000 data breaches. With Oracle Security, not only does it offer you greater agility, flexibility, and scalability, it also puts security first. Security that's automated, always on, and architected in, protecting data throughout its life cycle and across the full stack. That's Oracle Security.
They don't come back. But for IT, it is quite different. I talk to a lot of companies where they have these workloads that are up and running that are maybe only used at the weekend for batch processing or maybe only used in working hours, but they have experience, and so they know that if you turn it off and on again, it might be quite different when it comes back up, and it might not even come back at all, and someone's going to have to work for a while on it. And so it's just too scary to turn things off. So I think this is something that we can work on to fix. And if we get that automation in place, so it could be something like GitOps, but it could be something simpler. There's another benefit, which is now you've got your disaster recovery, because you're sort of simulating a disaster every time you turn it off. And so that means that if you do get a big disaster, you've got the automation in place, you've got the scripts in place. But of course, for us to be confident turning things off and on again, it's got to be fast. You can't have it like, I turn it on and then 20 minutes later it's good to go. It's got to be, I turn it on and it's there. And it's got to work, and it's got to work reliably. And at a technical level, there's 2 things that you need for this to happen. One is idempotency, which means that if you turn it off and on again and it loses its state, it basically behaves the same. If you send it multiple requests, it behaves the same. And the other is resiliency, which is, again, something that you want to be achieving anyway. So I've started to talk about this idea of turning things off and on again and having it actually be something that we're safe and that feels comfortable as light switch ops. So far, no one else is talking about light switch ops, but I keep hoping that if I say it enough, somewhere someone's going to start talking about light switch ops as well, and then I'm going to be like a thought leader, and I'm going to be like, job done. So that's sort of part 1, is think about the elasticity, think about your infrastructure, try and get it so that you can turn your infrastructure off, whether that's Kubernetes, whether that's hardware, whatever it is, when you're not using it. So then the next part is the application itself. So your code and all of the software that it runs on. How can we make that as efficient as possible? An obvious thing to think about here is, well, what programming language should I use? because probably some programming languages use less energy than others. Anybody want to have a guess what programming languages use the least energy? Oh, I heard assembler, and assembler is an awesome one because I think you're right and I don't know. I don't have the data for assembler, but yeah, that is a good one. Someone else said C, yeah, definitely. Yep, gold star for C. Any other thoughts on what might use less energy?
Java's pretty low.
Yes, you've been paying attention. Any other thoughts? Was that Python? No. So, yep, that leads us neatly to what programming languages use the most energy. And I'm sorry to say, but we'll just pretend that I'd advanced the slide a little bit earlier and you're answering this one. So well done. Yes, Python does use a lot of energy. So this is the section where we get to hate on all of the programming languages that aren't the ones that we use. So any other thoughts on what languages use a lot of energy?
Ruby.
PHP, Ruby, yep. Was that Java? No, interesting. JavaScript, less than you might think, actually. Yeah, JavaScript has really interesting energy and performance characteristics. But yeah, so I think you've got most of them. One that didn't, yeah, so this is the paper that has one set of answers based on, they had to use benchmarks that they could use across all 27 languages, and they looked at 27 languages. So that does, I think, sort of limit how broadly you can go from these results to making your plan for life. But what they found, sorry, that is completely illegible. Yeah, so this is normalized, but the first thing to take away is there are big differences. So C is 1 on this graph. Rust is like only a touch more than C. Rust is incredibly efficient. Java is about 2. So Java, considering how much Java does for us, is really incredibly efficient. I am a Java developer. This is the jug, so this means that we can all feel really good about our life choices. Java is an okay choice, because even if I wanted to save the world, I would not go away and rewrite the applications that I currently write in Java in C, because by the time I debugged them, I would have used so much more energy than I ever saved by writing them in C. So it is a good choice. The other interesting thing here is that Go, which Java is compiled to bytecode, Go is compiled, and Go actually uses more energy than binary, even though it's a newer language, even though it's compiled, it uses more. And you can see JavaScript, as you'd expect, JavaScript is kind of not great, but it's also much less terrible than you might expect, considering how much we all love to hate JavaScript.
Let's face it, with traditional recruitment agency models, you're exposed. If a candidate leaves any time during the first 12 months, you and your team will experience major pain. That's why at Stack & Co we've created a win-win risk-sharing hiring model where we share the risk with you for the first 12 months and allow you to spread your hiring budget out over that time period. Furthermore, in the unlikely event of a Stack & Co candidate leaving any time during the 12 months, the payment obligation stops. Being software recruitment experts, we'll introduce you to the best engineering talent available in Ireland today. Reach out to me, Jerry Nolan, for more information via our website, stack&.co.
And here's the full table. So you can see a few other things. So like anything starting with P, basically, yeah, Perl, Python, PHP. So those are expensive languages. And you can see Java is number 5. So has anybody ever programmed in Ada? No, I have never met a human being who programs in Ada, so I think we can rule that out. So the only languages that are more efficient than Java are C and C++ that none of us want to use, and Rust that is specialized. So we are in a good place. But then it sort of gets more interesting as well, because if you look at the energy efficiency of Java specifically, There's a paper where they looked at how much, how you can tune the JVM to make it more efficient. And the thing that was really interesting to me about this wasn't the specific parameters that they chose, because that's going to vary depending on what workload you have. What was interesting was that they said they could change the energy efficiency by 100% based on their choice of JVM and their choice of JVM parameters. So that means, going back to there, Java is half as efficient as C, but there's a factor of 2 in Java. So probably with the right tuning, we could make Java so it's even more comparable to C while still being as delightful as Java. So then the next question is, wow, like if JVMs, they have a pretty standardized set of things that they do, and if even the JVM tuning parameters can make 100% difference, how much difference does the framework make? And this is where Quarkus comes in. So as we mentioned in the introduction, I work on the Quarkus team, so this is of course something that I'm interested in. But Quarkus, we describe it as supersonic subatomic Java. And what we mean by that is it's really small and it's really fast. Here's the sort of the figures we share. So you can see that compared to a traditional cloud native stack, you're looking at, like, depending whether you run it as a natively compiled binary or on the JVM, you're looking at either half the memory footprint or like 1/10 of the memory footprint, and the same on the startup speed. You've just got so much more startup speed. Another thing that we don't show here is that the throughput will also be higher, certainly if you're running on the JVM. So we kind of intuitively felt that if Quarkus is so small and fast and light, that must translate to a lower carbon footprint, right? But we didn't actually have the data to show it. So one of the things that I did when I joined the team is I set out to actually gather the data. It turns out measuring carbon's really hard. And I'm going to share this partly so that you can all feel really sorry for me, but also because this may be interesting to you if you want to do similar exercises for your stacks. In principle, it's really easy to measure carbon footprint. The first thing that you do is you just have to measure the power usage. And so you can get things that you plug into the wall, and sorry, that is also impossibly small, but basically it's saying you plug the thing in at the wall and then you see how much power is coming out of the wall. That's how much power your workload is using. That gives you a really thorough answer, but the problem with it is you have to have access to the wall, to plug the thing in. And it's not integrated in any way with any of the benchmarking or monitoring or anything solutions that you might already have. What a lot of people do instead is they look at the CPU, because the CPU now, most CPUs can tell you how much power they're using. And Intel have this thing called RAPL, which tells you how much power the system is using.
Every clinical trial starts with a question. At Teckro, we asked, why is it so complicated to run clinical trials? We asked, what if? What if you could see who is interacting with your study in real time? What if you could be certain site staff always had only current, approved documents? What if you could proactively implement improvements based on site feedback? What if you could deliver tailored messages with the right information at the right time for the right people? We transform your paper protocol into a digital hub of communication and collaboration. Teckro is a single cloud-based platform that provides all study stakeholders with the knowledge they need when they need it, even at the point of care. Today, Teckro is used by large pharma and emerging biotechs to manage trials around the world, supporting all therapeutic areas, all phases, and any trial model. Simple, intuitive, and easy to use, there's no doubt why site staff around the world rely on Teckro, the hub for communication and collaboration. Study answers neatly in your pocket. Have a question? Teckro the answer. Visit teckro.com for more information.
is using. So this is nice because you can access it programmatically. If you're doing some benchmarking or something like, or monitoring, you can hook it in so you get all of your information in one place. It's not bad. One thing that both of these will exclude is the cost of your network traffic, because data costs carbon. So that it sort of excludes that. So that's something to bear in mind. But of course, in 2022, there is a problem, which is that most of us don't have our data centers physically accessible to us. Most of us are running in the cloud. And by definition, the cloud is a black box. That's kind of the appeal of the cloud. So we're sort of limited in what we can do. The good news is if we have the load information, we can get a lot of the way there. So there's a company called Teads, who weirdly are an advertising company. So I don't know why they've done this piece of work, but they've assembled this huge data set. And if you have heard of something like the cloud carbon footprint, that is based on this data set. So the Teads data set allows us to convert from load to power consumption. Once we have the power consumption, we then have the next extra step, which is to convert that power consumption to carbon. That's going to depend on what the energy mix is. If it's coal, it's going to be a lot more carbon than if it's solar. That will depend on what region we're in. There's published energy mixes for most cloud providers for most regions. Most of them haven't been done with an open methodology, and they're not consistent between them, so you can't really compare across cloud providers very well, but it allows you to at least get something. And the final thing that you need to think about is the embedded carbon. So that's the carbon in the actual hardware, because even if you're running on 100% green energy, a lot of carbon was used to manufacture the equipment. So things like mining for the minerals, things like the power that powered the factory where it was produced, the shipping that was probably done by a lorry using fuel. So you need to take that into account as well. But again, you can do that with the Teads data set. The downside with all of this is it's a lot like hard work. I can see a whole bunch of sort of faces going, ugh. So there are some simpler models. So one is the Vroom model. I made this name up. I don't know what it's actually called. And it's also a little bit wrong, but I'll come back to that. And this is the idea that basically the faster something is, the less carbon it uses. So if you go back to that comparison between the programming languages, on this column, it is completely illegible, but on this column is the time. This column is the energy. This column is the time. And you can see that the ranking is pretty similar. So like Rust is 1.03 on energy and 1.04 on time. And if you go down, you can find a few bits where they're different, but like they're really similar. So there is a useful rule of thumb, which is that energy consumption is proportional to the execution time. So if you have a really slow job that takes forever, it's going to use more energy than a fast job, assuming you keep other things the same. If you like apply way more hardware to it and then let it use twice as much memory and give it more cores, obviously then everything is out the window. But if you keep things mostly the same, then you can use how long something takes as a guide to its carbon footprint. Another useful model is the economic model. And this name is the Economic Input-Output Lifecycle Assessment. If you actually try and look this up, I promise you, your eyes will glaze. Do not do that. But what you can take from this is that if you reduce your cloud spend or your hardware spend or your electricity bill or any of those things, and you keep everything else the same, then you're reducing your carbon footprint. if you don't need an exact calculation, if you just need to know you're going in the right direction, this is really useful. And it's information that you hopefully have already, unless you don't have your FinOps sorted out, in which case you have no idea. So I mentioned both of those models. Whenever I show them to people who actually know what they're talking about, they get really upset and they say, oh, but no, it's, this isn't right and this isn't right. You can definitely find things that break both of these models. But as a heuristic, as a place to get started to do something which is better than doing nothing, it's useful and it's information that you already have. So using these models, what did we see with Quarkus? Well, about a year ago, a colleague did do some experiments where he was looking at how much Quarkus costs. So he took some cloud instances and he ran a workload for 20 days and he just tried sort of a traditional cloud native stack, and he tried Quarkus running as a natively compiled binary or Quarkus running on the JVM, because you can run Quarkus either way, and to see what the cost was. And what he found was that the cost of Quarkus was about half the cost of running your traditional cloud native stack. And the cost of running it on native was about the same. You had to have the same size instance for a natively compiled binary. It would start really fast, but for the sustained workload, you needed the same size instance. So with this information and the TEEDS data set, I was able to then go and get carbon metrics. And you can see here's the economic model kind of in action, because like those two, the bars are carbon and the lines are cost. They don't match exactly, but the direction of travel is the same. So you can see that that Quarkus has about half the carbon footprint of your traditional cloud native stack. So just switching to carbon, I cannot tell you how hard it is to talk about Quarkus and carbon repeatedly without getting into Quarbon and Carcass, and it's bad. So native seemed to have a slightly smaller carbon footprint, but we couldn't really, because of the granularity of the instances, we couldn't get the data to show that on the data. It looked the same. So this year, in the performance lab, we did a set of experiments that were specifically looking at carbon. So on this experiment, what we did is we just fired in as many requests per second as it could eat. And the line on each of these, the line drops off when it kind of went, oh, please don't send me any more load. I am done. I can only do this much load. So what we've got, so basically lower lines are better because it means it's using less energy and less carbon. And lines that go over here further show a runtime that was more capable of dealing with load, that had higher throughput. So you can see Quarkus on JVM was the best. Quarkus on native was the second best. Legacy on JVM was next, and legacy on native was really pretty inefficient. That was just for a single instance. So what if I want to have more load than 20,000 requests per second? Then I need multiple instances. And when you do that, you get this nice clear graph where you can see, again, on this, higher is worse. So Quarkus on JVM had a much lower carbon footprint than the others. Quarkus on native was next. So here, again, we see a reduction of about 2 or 3 for in carbon for Quarkus. But interestingly, native consumes more carbon than running it on the JVM. And I'll come back to that. So the sort of the TLDR for all of that is, does Quarkus reduce carbon emissions? Yeah, it absolutely does. Just sort of for free, automatically, it will go faster and it will save money and it will cut carbon. I do want to sort of give you a caveat here, which is sometimes people come to us and say, I ran Quarkus and it was slower. And then we kind of go, why was it slower? What happened? And sometimes it was like an edge case, or sometimes they had some path that had a defect. We've tried to run the most representative benchmarks that we could. We see in general from our customers that they come back to us and say, hey, I was able to save half my resource usage with Quarkus. So we're pretty confident in this. But if you have one of those ones where you switch to Quarkus and it's going slower, that's probably a good indication that actually you're also using more carbon. So, that's something to look into. Don't just go, oh, it's running slower, but I'm saving carbon, because it's probably not. I mentioned that native, the results for native sort of contradicted each other between the two experiments, which is kind of interesting. It's the sort of interesting thing that makes life interesting. As a reminder, there's sort of a really good blog if you want to read more about Quarkus on native. But in general, we sort of say for Quarkus, you should run on native, where you get those super, super lightning fast startup times. If you don't have super high throughput, or if you want to run on older hardware or hardware that's really resource constrained, or if your application is getting deployed all the time so it doesn't have time to warm up, or obviously on serverless. You should run on JVM if you want to maximize your throughput. We see throughput is usually about 10% higher running on Quarkus on JVM compared to Quarkus native. So Quarkus on native starts up super fast, but there is a little bit of a throughput penalty. If you know you're doing the deploy every 6 months, and you start your application and then you leave it go for 6 months, you don't care about startup time, honestly. So go for running it on JVM because then you get the higher throughput. Again, if there's no reason for you to be taking down your instances, maybe JVM is best for you. So that's sort of general advice. If you want to optimize your carbon, that's the advice. Those two are exactly the same. So really, if you try and optimize your cost, if you try and optimize your application performance, you're probably already doing the right thing for carbon. The good thing about Quarkus native is that it's not like you have to choose, do I want Quarkus on native or do I want Quarkus on JVM? It's just a compile time flag between the two. So you can have a hybrid model, you can change your mind partway through, and the application code will be exactly the same for both. Another thing to think about is command line interfaces. So we talk about native as being really good for serverless, and I hadn't realized until someone pointed it out to me. Native is also really good for writing CLI. So you can write a Java CLI, compile it to native, and it can do things like tab completion. Because it's so fast that when you hit tab, it will start up, figure out what it should tell you, and then shut down again. So you can do some quite cool things with that. And I don't have the data to show this, but I have an idea that a CLI is probably a pretty carbon efficient way of doing many tasks. So maybe that's something to also look at is, could I do more on the CLI and less with big UI frameworks? And maybe that would be a saving. I don't know. I've mentioned Quarkus native a few times, and I did show those figures at the beginning. If you compile Quarkus to a native binary, it will use less memory, and it will also start in around 0.01 seconds. So it's basically about 10 milliseconds. That's actually faster than an LED light bulb starts. So it looks instantaneous, and it really is instantaneous if you compare it to something like a light bulb. And I think it's easy to go, wow, it starts so fast. That's amazing. That's going to save me carbon. But an app starting fast isn't elasticity unless you also have the other things around it, like the resiliency, like actually having the processes to stop the applications. So you really need to think about that sort of whole picture of not just this starts really fast, but I never start it, but this starts fast, which enables me to stop it more often, which enables it to be off more of the time. And that's where the savings comes from.
I was really into science, and I kind of wanted to be maybe an astronaut or work for NASA in some capacity. We grew up watching Star Trek, Stargate, Red Dwarf, all these different programs. I think Stargate was probably the biggest influence because there was a female character in that was one of the main leads, and she was a physicist, and so it kind of made you think like that's possible as a female. So I went to uni and did physics with astrophysics for my degree, and then I decided to keep going with that, and I stayed in academia to do a PhD. Astrophysics isn't as far from software development as you might think. It's really about solving problems using mathematical skills and software development. I ended up being really more passionate about programming and solving problems that way than actually about astrophysics. I just started applying for jobs in Belfast for software development, and I found Liberty IT. They took people from a background in STEM subjects, so science, technology, engineering and maths. Liberty's focused on diversity and diversifying the workplace because they realise that a diverse workplace actually is better at problem solving and better at coming up with solutions for the customer. So my previous life as an astrophysicist might seem worlds apart from my career in Liberty IT, but the skills I learned just generally solving problems on a daily basis has really helped me in Liberty IT, and I've used it every day.
So when we think for Quarkus in particular, but I think this is probably true for other carbon-saving technologies, about where the benefits come from. The energy usage is lower. That's just a passive benefit. All you have to do is use Quarkus and your energy usage is lower. But if you go further, these are things that you actually have to take advantage of. You need someone to make the change. But you can run on a smaller machine than you were used to, and that's going to save carbon. And you can have that elasticity and stop your instances without needing to keep them up just in case. And again, that's going to save carbon. So these are all sort of benefits to think about when you think about the whole picture of how am I going to reduce my carbon footprint. And overall, I think it's useful to sort of bear in mind this model as well. And I think one thing that's kind of a bit counterintuitive with this, and I mentioned this with the Vroom model, is a while ago I had to buy a new car, and we had sort of a really tough choice because it was like, oh, I want to buy the one with the big engine that goes really, really fast. And then it was like, oh, but that would be so irresponsible. Instead, I'm going to buy the one with a small engine that goes put, 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 but I'll feel really virtuous when I'm driving it. So we have this kind of sacrifice and trade-off where we have to say, do I get the car that's really cool, or do I get the car that makes me a good person? But with software, it's completely not like that. Because with software, if it goes faster, that means it's more carbon efficient, which is kind of awesome if you think about it, because it means you get to choose the shiny toy that like goes really fast, and you're also saving the world. And this is what's called a no regret solution. So instead of sort of saying, oh, I'm going to do the really tough thing, you go, yeah, I'm doing the really tough, well, I'm doing the good thing, and yay, I won. They're also called, I keep looking for the right word for this, so they're also called co-benefits. I like to call it the double win, but you could also call it win-win, or win squared, or 1 + 1 = 3, or the twofer. Someone suggested I should call it the Überwinden, which sounds really cool, and it's got the word Uber in it, and you get to use umlauts. The only problem with it is I think if you actually know German, it doesn't actually mean anything particularly, yeah. See, it's so good except for when it intersects with reality. So I'm not going to use that one, but I still liked it because it looks cool. Sometimes I call it the extra win. But with all of, no matter what you call it, the idea is that if you do the climate solution, it makes everything better. And we can quantify it. So if we think again about those zombie servers where 25% of them were doing no useful work, there was another study where they looked at it and they said that the cost of servers was 26.6 billion that was wasted just in 2021. So that's public cloud spend. That's stuff that shouldn't have even been running because people forgot to turn it off or should have turned it off, that kind of thing. So that's, if you imagine what we could do with $26 billion, we could do so much. And so, yeah, basically, turning things off can save a lot of money. And we see this all across the board with these kind of solutions. So like at the moment, renewable energy is 9 times cheaper than coal energy. We don't have enough, which is why we have to run coal, but like it's so much cheaper. And if you look at it for cloud, if you host in Finland, it uses 43% less carbon than running the same workload in London, and it's 15% cheaper. So it's like the win and the win. And we see this with Quarkus. So I saw this and I saved it because someone just switched, and they were so happy because things were running faster, and they had the developer joy and everything else. And I liked this tweet because this is someone who talks, he's the one who I learned no regrets from. And someone sort of said, like, all of these things that I thought were going to be really tough choices, like switching to an electric vehicle or using a heat pump or actually having cities where I can walk around instead of having cities that are full of cars, that's actually better, and it makes me happy. And so I like this last line, which is, it's not sacrifice, it's advancement. Our technology is getting better and it's lower in carbon, but we also have other benefits as well, which I think is really positive and really hopeful. So to wrap up, do choose your hosting wisely, look at where it is. You have buying power because you work for a tech company. Use that buying power to encourage the businesses that you deal with to make greener choices. Turn things off when you're not using them. It's like your mom going, turn off the lights, but like do that for your IT and there's a big savings. Choose an energy efficient framework because you will see non-trivial gains from doing that. And with all of that, this is something that's going to make you happier and better off anyway. So that's good news. And there are the slides. And with that, thank you very much for 2 talks.
Well, Holly, that was amazing, actually. I learned loads from that.
Thank you.
The only thing I can say about the little sign in the toilet is we need to get people to read it.
Oh, do you find it?
Yeah. So, but anyway, that's how. Did we all have a great time tonight? Yeah. You're more than welcome to hang back and have a couple more drinks. It's completely fine. I don't think it's raining at the moment. But if it is, and it's windy, I want everybody to arrive home safely. Okay? Pledge. Safety! Okay. So, again, thank you very much to all our partners. And...
I can do this, I can do this, I can do this.
Yeah, thank you to all our partners. They really help us keep things flowing and everything, so it's fabulous. You can see who they are. You can also read about them on our website, which is great. And next event. Who wants to know about the next event? Hey. Okay. We have...
26.
You know more than I do. I need you to come and be on our team, I think, actually, because I wouldn't remember that. Is it 26?
I think so.
Yeah, I know it's a Wednesday. Because every dog joke is on a Wednesday. It's Maurice Naftalin from Edinburgh is coming over. And we're going to be doing the evening gig, but we also might be doing a workshop during the day as well. Okay, so you have to speak to your bosses nicely. I forget now what he suggested, but when I read it, I was like, that's pretty cool, you know? So anyway, so keep your eyes on the emails that we send out to there. You can also subscribe to the LinkedIn Dubjub group as well. I think we're on Facebook. We're definitely on YouTube. Okay, so that's it. I think we covered everything. Holly?
I think so,
How's that
yeah.
wine going? You're drinking very slowly there.
Oh, well, yeah.
Yeah?
Can't drink and talk at the same time.
Okay.
I need to fix
All
that.
right, great. Does anybody have any questions they'd like to ask Holly? No? Frazzled.
Yeah.
Thank you very much.
Yeah. Thank you all.
Oh, sorry. Oh, the 23rd. Okay. Dennis?
Quite depressing thinking about all the